Looking forward, we have a chapter 7, external flow, then an internal flow. So this is inside pipes and ducts. This is over cylinders, spheres, over flat plates. And then we move into chapter 9 with natural convection, then heat exchangers. And I think this is the shortest time between exams in this semester. So before you know it, we'll have another exam. It'll be exam 3, and it'll cover those chapters. All right? All right, let's jump into it. Okay, this class is not hard. It's actually very easy. Heat transfer is easy. The hard part, though, is the prerequisites. And the prerequisites of all the math, all the differential equations. That's been a challenge so far. Also, for today, it's all fluid mechanics. It's all fluid mechanics. And so most of today's lecture is simply a review of fluid mechanics, and then we add a little bit to it and call that heat transfer. And it's external convection heat transfer. So if you focus on it, chapter 7.1, this section is empirical, meaning we're going to rely a lot on experimental observations and a little bit about what it means to have empirical correlations. And then talk a lot about flat plate. Well, you've studied flat plate in fluid mechanics. That's what we're going to spend a lot of time reviewing, the Blasius solution. And then when we get to our convection coefficients, don't try and give answers to 3 and 4 and 5 significant digits. A lot of these correlations are plus or minus 25%. That's the nature of the beast. And then we're going to talk about, this is a very nice section, 7.3. It's basically, how do you solve these calculations? How do you do convection heat transfer calculations? And that'll be a good summary. I encourage you to read it. And then we'll talk about external flow over cylinders and spheres and then call it quits. I don't even do tube banks. There's time. I don't have time to cover all of the external flow conditions. So last time we talked about the boundary layer equations, the continuity, the momentum, the energy equation. We talked about the shear stress. We talked about the friction coefficient. We talked about the convection coefficient. We talked about the Nusselt number. Notice this is dimensionless. This is dimensionless. And basically H cast in dimensionless terms is the Nusselt number, and tau, the shear stress, cast in dimensionless terms is the friction coefficient. And hopefully you see the patterns. We had an analogy between the momentum transfer and the heat transfer, and there was our analogy. It has not only Prandtl number restrictions, but it also has other restrictions that we emphasized, and I'll re-emphasize those restrictions because we will use that analogy today in some cases, but not outside of other cases, not all cases, because there are restrictions. So an empirical correlation is a correlation that has been promulgated by the president or the king or dictator or whatever, or it's been inferred by experimental measurements, or determined by analytic methods, or developed in the English-British system of units. What is it? I'm going to throw up more clicker questions today than I have time, so get ready, but what is the answer to this without clicker? B. It's basically the whole idea of that first section of this chapter is it's based on experimental measurements. A lot of correlations, that's how they got them. Not sophisticated analysis methods. But some of them are based on analytical, but not all of them. Majority are based on empirical measurements. All right, so let's go back and review a little bit about solving for the velocity profile over a flat plate, fluid mechanics. We had this equation and this equation. They're both what we call PDEs, partial differential equations. We use them to solve for the velocity field, the vector field, which is ui plus vj. It's only two-dimensional. And so we're really looking to solve for u as a function of location, both in the x and y, and v, that y component of velocity, as a function of x and y. So it's like it has both u and v as unknowns, and both u and v are functions of x and y. And so just for the flat plate, where we have x going from 0 out to L, the end of the flat plate, it can go off to infinity, but the flat plate ends, and that's where we stop our analysis. And then y goes from 0 out to infinity, the free stream. So we can talk about our boundary conditions on velocity, and we have our governing partial differential equation. You're ready to go and solve for that velocity field and do a good job of solving for it. Well, this is a very challenging problem. And in every fluid mechanics textbook that I know of or looked at the college level talks about the Blasius solution to this problem. A person named Blasius did it, and they still talk about it today. So let's jump into what did he do. But before I do that, I have some clicker questions. So when we're going to cover the Blasius solution to the boundary layer problem, flow over knife edge flat plate, we're going to solve these two equations, right? These equations, true or false, assume that the fluid is incompressible, true or false, and I'll give you only about 15 seconds or 10 seconds. And let's take a look at our results. And everybody says, or most of us say, yeah, this is for an incompressible fluid. That's definitely true. There's no density variation in it. All right. How about the next one? Do these equations, as written, assume that the flow is steady state or not? So where in the equations is a partial with respect to time? And when you see a partial with respect to time, that means, oh yeah, something's changing with respect to time. But there's no partial with respect to time in these equations. It's only going to solve for the steady state velocity profile for incompressible substance. So that's true. A laminar flow, these equations as written allow us to solve for laminar flow. What happens, somebody says, well, can't I use them to solve for turbulent flow? Well, what's the idea behind turbulent flow? If I go out at a point, this is the knife edge flat plate, at this point right here, at some instant in time, the velocity may be like this, or it may be like this, or it may be like this, or it may be like that. Time averaged, it's a steady value with one direction and magnitude. But at an instant in time, in turbulent flow, it can be all over. This does assume, and only good for, laminar flow. Somebody says, well, let's use a fudge factor of some viscosity that I adjust to account for and make it look like. Well, okay, that's an approach to solving the problem when you use some eddy viscosity. But all right, do the equations right there account for free stream pressure gradient? So if somebody says the free stream pressure, what is that? Would that be P infinity, just like the free stream velocity? And then somebody says, well, the gradient of that free stream pressure, would that be dP infinity dx or dP infinity dy? But is there any dP dx anywhere in the equation? So what does it assume about that? That P infinity is equal to a constant. That's what it assumes. That's what the only thing we're solving. We're not solving for where the pressure gradient's making it accelerate. So let's see how you did. These equations, well, I wish I could make this box smaller. Do they account for free stream pressure gradient? Do not. That's false. All right. In the equations, as shown, the velocity boundary layer, that's what we're going to be solving for, is a function of or depends on the temperature field. So let's take a look. It does not depend. There's no feedback mechanism as shown. In this equation right here is mu over rho. Isn't that our kinematic viscosity? And you're saying, but everybody tells me that and my experience tells me that the viscosity is a function of temperature. But when we solve it, we're not solving for nu varying. We're solving for a single value of nu, meaning single value of viscosity, meaning no temperature effect. That would be the most likely effect of temperature feeding into this equation. But no, we're not going to do that. So there you go. Let's press forward. In the textbook, as well as almost every fluid textbook I've seen, the Blasius solution is given. It's outlined. It's sketched. In this textbook, it's in 7.2. The details are tedious, super tedious. The guy Blasius was a genius to first come up with this, okay? So what I'm going to do, I'm just prepping you, the next slide's going to overload you. You can't take all these notes. Just say, I'm going to get the idea, because I'm going to be reminded of the Blasius solution that I've seen already in fluid mechanics, but I'm going to get the idea again, and the details, I'm going to go to the textbook, not this lecture right now. There you are. What are we trying to solve for? Two PDEs, the continuity and the momentum equation. Okay, we're going to be especially interested in what's happening at the surface, that gradient, so we can get the shear stress. We introduce in fluid mechanics the stream function. If you could find the perfect stream function such that u is equal to d psi dy and v is equal to negative d psi dy, it automatically satisfies the continuity. I've knocked out one of my PDEs. I'm down to only one PDE. But I assume the solution's in the form of a stream function, which I haven't solved for yet. Then we come up here and we say these equations look very similar. The profile, the velocity profile looks similar, so you introduce a similarity variable eta. That's the genius of Blasius. As well as we're looking for a similarity function of eta, where you have the stream function divided by its normalized. Okay, you take the one remaining PDE, the momentum equation, and you work with these definitions, and you say u is going to be df d eta. That's not trivial. That's a lot of work. And that's probably the easiest of them. But you're going to take this PDE and convert it into an ODE, and then you're going to solve it. But you're making it a little more abstract. Likewise, you convert du dx into that term. The book does the details blow by blow, but believe me, it's a chain rule on steroids, calculus on steroids. Got it? Okay. And then you do that, and I've shown that kind of in Cliff Notes version right here. Then you simplify a little algebra, and there is a brand new ODE. You look at it, and it gives you tremors. It's like, I don't like even second order ODEs, but this is now a third order. And I'd like everything linear, but look it, I have f times the second derivative of f. That's a nonlinear. I don't know if it's improved the situation or not. Blasius thought he did, and we still talk about it today. Now you transform your boundary conditions, and because it's third order, I need three unique conditions to go with my third order ODE. Then I can say, let me solve it. Let me now solve the ODE. Well, how are you going to do that? A numerical solution is the way to go. Yes, there's some analytic solutions, but they involve a series, and then it gets very complicated. So here's the summary the textbook provides. So as a function of eta, you solve that ODE for the similarity function f. The first derivative, because we're going to relate that by definition to the du d u infinity, so it's a normalized velocity in the x, as well as of interest to us is the second derivative of f with respect to eta. So you get all of this, and you fill up a table, and you can go to 7 or 10 or whatever, but you stop the table at some point. And then you take a look and you say, u over u infinity, when that's equal to 99%, that means u is equal to 0.99 of u infinity. Hey, that's the thickness of the boundary layer. And so Blasius' solution says that the derivative of f with respect to eta. So you find where's the derivative of f with respect to eta equal to 99%. You come over and find eta. Eta is around 5. Eta is around 5. At that distance, normally there's a y right here, but it's at that particular distance, y equal to delta times the square root of u infinity over nu x. You then have now one of the big conclusions that the velocity boundary layer thickness grows like that. It's 5 times x, the distance from the leading edge, over the square root of the Reynolds number at that location. This is a big conclusion in every fluids book. All right, then not only do we have the growth of the boundary layer, we can go and talk about the friction at the wall and the skin friction coefficient. So you say, well, what was the law of viscosity evaluated at the wall that give us a shear stress? Okay, using our similarity solution that devolves down into I need to get the second derivative of F with respect to eta at the wall. I come over here, I say at 0, here's the value of F, here's the value of the first derivative of F, and there is the second derivative of F at the wall. So I put in right here 0.332. And I do some algebra, and I normalize C sub F, or I introduce C sub F, which is a normalized tau, and do some cancellation, and here's another big equation that's in every fluid mechanics book. The growth of the thickness of the boundary layer, and then what is the local friction coefficient? It's at coefficient 0.664. Somebody says, well, I think it was 0.332. Well, some books put the half on in front of the C sub F, some don't. You just have to watch out for that. And it's times the 1 over the square root of Reynolds number. Okay. You're not done. That was all the prerequisite material. Now let's get to some heat transfer. Well, what is our energy equation look like? It assumes incompressible, steady. There's no viscous dissipation term. All you have is the diffusion of heat through the temperature gradient and the Fourier's law. And you have the advection of energy and the convection. Okay, you cast it in dimensionless terms, and when you see 3 dots like that, you can just think of a lot of work because you've got to take that solution for U with that similarity in the stream function, and then you have dt dx, blah, 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 all that, and you work out and you find a new ordinary differential equation where you're now bringing in U, the solution of the velocity field, into it, and there it is. Let's take a look. Well, look, second order in this dimensionless temperature. Temperature is a function of eta, similarity variable. We have a Prandtl number, that's just a property, nu over alpha. We have F, that's like the velocity function, field impact. And then we have the first derivative. So you bring this in from the Blasius solution. There's no way to do this analytically, or somebody probably did, but it's a series solution. You do it numerically. And then you can solve with these boundary conditions, solve that ODE. What you're interested in is H. Well, what is the definition of H? How do I get the gradient of the temperature at the surface? Well, it's going to be cast in dimensionless terms, and then from the numeric solution you find, only for a limited Prandtl number, you find 0.332 Prandtl to the 1/3. So once I have H, then I can put it into the Nusselt number, do a little algebra, get this out of the way, and there's our big result, that you can get an expression for the local Nusselt number, which is a function of the local Reynolds number, and then you have this Prandtl and a coefficient. Somebody says, that's the value at X. How about give me the value averaged from 0 to L? Well, you would just say 1 over L, the integral of the Nusselt at X dx from 0 to L. Okay? So, for the momentum transfer, you were able to work out from Blasius' solution this very important result. As well as when you do for the heat transfer, I didn't show the details, you can come out with this result for the growth of the thermal boundary layer. It's related to the growth of the velocity boundary layer, but it's multiplied by Prandtl to the 1/3 power. Okay. if it's turbulent flow, forget Blasius. It was only good for laminar flow. So what do? Well, a lot of people have made a lot of measurements, empirical correlation, fit, and they report that this is a good curve fit, empirical on how the boundary layer continues to grow, the velocity boundary layer. That's in your fluid mechanics book. If you think about it, once you're turbulent, it's being mixed like that. It's not how viscosity competes with thermal diffusivity. And so the thermal boundary layer and the velocity boundary layer are essentially the same. There's no difference. They have the same growth mechanism or transfer mechanisms. It's mixing. So this is a big result right here. It's only for laminar flow that you can get a difference. And if the Prandtl number is around 1, they're the same anyway. For gases, guess what? Close enough to, it's a little less than 1, but it's close to 1. All right. We add to this table. We're going to add to it, we're going to talk about the information from the momentum transfer and heat transfer for both laminar and turbulent flow. We're going to talk about C sub F, the local friction coefficient, and NUX, the local Nusselt number. And then we'll do the same thing down for turbulent flow. So let's just summarize what's in the textbook. Here it is. This is the result. Where did that come from? Blasius solution. If you then take it to turbulent, where did this come from? Experimental measurements. There's no way that Blasius extends out. Oh, I'm sure somebody did that analysis and fudged it with the coefficient, but no, experimental measurement. What about this one? Well, that was from the extension of the Blasius solution analytically that we just covered. And then this one right down here is hard. But you know what they did? They used the modified Reynolds analogy to take this result from the friction coefficient to the heat transfer. So I just expand that just a little bit. So this is our modified Reynolds analogy. We just take the 1/2 C sub F, the local friction coefficient, multiplied by Reynolds and Prandtl to the 1/3, and there's our correlation for the Nusselt. There are some limits. Anytime anybody quantifies empirically, correlation, they say, hey, I looked at a lot of data and it's in this range of Reynolds number. Hey, what is the critical Reynolds number for flow over a flat plate? 2,300 or 500,000? Yeah, 500,000, 500,000. So you get that same result. Not only can we get the local, we can do the average, local to average for those Nusselt numbers. That's okay, you can do that. That's done in the fluids book and also in the heat transfer book. Sometimes we want a local value, sometimes we want the average value. So we have covered a lot of ground, but don't forget that these correlations are plus or minus 25% when they're based on the experimental data. Or if you don't know your fluid properties that accurately, well, even an accurate analytic solution isn't going to improve your uncertainty in the properties. Now let's take a look at this section, methodology for doing these type of calculations, because this is a little different than conduction. And I do like this section. I think it's a useful section. Probably the first time you read it, you don't get much out of it, but the second or third time, and then you'll get more out of it. So here it is in summary. How do you solve convection heat transfer problems? First of all, some students will forget the flow geometry. Are they looking at analyzing flow over a flat plate, flow over a cylinder, flow over a sphere, flow inside of a pipe, flow inside of a rectangular duct like that, inside a pipe or whatever? And they have to get that straight because everything's based on the geometry. You have to go and find correlations and they depend on the geometry. Then it's fluid properties. I'm going to need to calculate that Reynolds number. Well, I need the viscosity. I need the density. Sometimes they're temperature dependent, especially the viscosity, not necessarily the density, but it can be as well. Okay, most of the time, you use a film temperature, which is so simple, does it even need to be explained? It's like, what is my surface? What's my free stream temperature? Take the average of them. Pretty straightforward. Sometimes you'd use a different strategy, but this is often used, a film temperature. Okay. If you see a mu sub s or a PR sub s, that's a key. It's a little red flag saying, okay, evaluate your fluid properties at the free stream temperature, and then every now and then evaluate it at the surface temperature for a particular parameter. Okay. That's what that S is on there for, at the surface, at the surface. Okay. Once you have a good idea of your fluid properties, you can usually calculate a Reynolds number to see if you're laminar or turbulent. The different things happen when you have turbulent flow inside of a pipe or over a pipe or over a flat plate. So basically find out that you're laminar or turbulent, because usually you have a different set of correlations. Then figure out, what are you asked to solve for? Am I looking for an average value or a local value? Different set of correlations. Then find your right correlation. A lot of them are this simple. I'm doing a heat transfer calculation, so I need the Nusselt number. And it's usually a constant, Reynolds to a power, Prandtl to a power. Those are the simplest, the most common. They only get worse than that. Once I have my Nusselt number, then I can unravel it, because Nusselt is defined as H. If there's a L here, L over K, then I get H is equal to the Nusselt, it's function L, times K divided by L. Haha. So it's like you've done these in drag and friction calculations in fluid mechanics. It's very similar. Now, maybe you use the H to calculate the Q, the rate of heat transfer from the surface. Or maybe you use it to solve for the unknown surface temperature. So a lot of times it's like, what is the unknown? Sometimes it's T sub S, sometimes it's Q. Let's say it's T sub S. Well, you're saying, hey, didn't I need to assume T sub S to get this process started? Yes. And then students brand new to convection heat transfer get stuck. It's like, hold it. If I'm trying to solve for T sub S, but I need T sub S to get the film temperature, to get the Reynolds number, to get the right correlation, to get the Nusselt number, to get the right H, to then solve for T sub S, what do? Guess and iterate. And you don't like that word right there, but right up here you may have to just guess the film temperature to start. And then, I now have a better value estimate of T sub S. Go back and revise the film temperature and do it again. And in my practice, you should do that a few times by hand, but then you'll find that it quickly converges. I've never seen really a need to go to 3 iterations. 1 or 2 iterations and you're there, but you should prove that to yourself. So this is why this is worth reading, because the roadmap gets a little tricky and then you have to iterate in some cases. Now let's review fluid mechanics. Let's talk about what happens when you have a cylinder in crossflow. So we have case 1, case 2, case 3, case 4, case 5, off of some NASA websites. So hopefully, but these illustrations are in every textbook in fluid mechanics. Okay, it's pretty common. So let's talk about it. Do they change the diameter of the cylinder in these 5 cases? Not really. Okay. What are they changing, these 5 cases? U infinity, the approach speed. Leave the cylinder at rest and then your approach speed. Which one has the highest approach speed, case 1 or case 5? 5. This is U infinity is very, very large. It's fast flow, right? And then this over here is very slow flow. Okay. Let me go and ask a clicker question. So we take a look at that first, that lowercase. What are the blue lines that are shown in this illustration for flow over a cylinder? Are they streamlines? Are they path lines? Are they streak lines? Or are they all of the above? stream, S-T-R. All right, I think everybody's in. Let's take a look. And come on now. There's no difference when it's steady flow between a stream, a streak, and a path line. Then you come back. Okay, everybody gets credit. All right, fine. But look at what are we doing right here? Look at this nice line right there. Look at the line right in here. What are they showing you right in here? What is that? It's part of that laminar versus turbulent, isn't it? Isn't that velocity is not a steady value in those locations? They're kind of jumping around. It's a wake. That's what they call a wake, right? W-A-K-E. Now there's some smoother transition. What is this right in here showing us for case 2? What is that? That they're showing us a little circle. It's a little recirculation region, recirculation. And then what happens is when the flow gets a little faster, what are they showing here? It's like little vortices that spin off. It's a von Karman vortex street. It's getting more and more unstable as the flow speed goes up. The Reynolds number is going up. And then they get where they have this big separation region. And now there's some very good structure in here with the recirculation. There's less structure to the flow, but there's still a pattern of this tail, this shedding vortices. And then you get this wake region but then you get this region, case 5. And what's the big difference between case 4 and case 5? Yeah, they have the word laminar right here and turbulent right there, but it's basically the size of the wake region, isn't it? Which one has a smaller wake region? Which one has a smaller wake behind the cylinder? Case 5. Case 5. So, take a look right here. We have low Reynolds number flow over a cylinder sphere. It's called creeping flow. It's also called either Reynolds, Bernoulli, Darcy, Stokes, or Mach. Now, I'm not going to give you the clicker question because this is an unfair question, but guess what it is? It's Stokes flow. This is the right answer. Maybe some of you would have remembered it, but that's okay. And now, if I have a cylinder or a sphere, and I have very slow flow over, you think, well, that's never happens. But it does happen, and there are some cases in practice. If you're interested in some settling out of small, fine particles in air, and it's stationary or stagnant air, you can find the aerodynamic effective diameter of that particle and consider it's dropping like a sphere, Stokes flow. It may take a long time for it to settle out. All right, now let's shift a little bit and talk about our pressures. Talking about flow and our velocities, now we talk about pressures. So let's say we're really focused on this first case, the slow flow. Don't worry about this, I'll get to it, right? And we've got point A, B, C, D, and E. See where they're located? So let's play this game. Let's just take a look at the pressure and say the pressure at point A compared to the pressure at point B. Pressure at A greater than B, equal to B, or pressure A less than B? All right, well, why are we not more correct? What's happening is that point B is called a acceleration point or stagnation point? Stagnation point. And when you bring your flow to the stagnation point, it comes to rest. And the pressure goes up. It goes up by the amount of the dynamic pressure, the velocity pressure, both names work, 1/2 rho v squared. Bernoulli's equation. True? All right, so there you go. Let's move to this one. Let's compare now B and C. Where is B? Right there, stagnation point. Where is C? In the flow right at the top of the cylinder. So is the pressure at B equal to, greater than, less than? What is it compared to C? All right, let's take a look at the results. pressure at C is lower than the pressure at B. Pressure at B is high, the stagnation pressure. Okay, let's compare the pressure at C and the pressure at D. All right, so, okay. The pressure, what's the difference between the pressure at B and the pressure at D? Maybe I have that down here. Maybe I should have asked that one first, right? Let's do this one verbally. Who's risky enough to yes, sir?
I think they're equal.
They're equal. That's right. For Stokes flow, for low speed creeping flow, they're equal. That's right. That's one of the conclusions. So basically, the pressure at C is low compared to the pressure at D, isn't it? So which one is right? All right. So let's do this. The flow moving from B to C, right? It's going from a high pressure to a low pressure. And then from C to D, it's flowing this way. It's going from a low pressure to high pressure. Is that true? That's what we just talked about, right? And that the pressure at B is equal to the pressure at D. Let me see if I have a question on next slide. I want to talk. Man, I need to talk about this. I need to talk about the pressure gradient. It's like I'm moving from high to low. Does fluid like to move from high to low pressure? If I have a pipe, I have high pressure on one end of the pipe, low pressure on the other end of the pipe. Which is the direction of the flow in the pipe? From high pressure to low pressure. That's the way fluid likes to go. Like temperature, hot. High temperature over here, hot. Low temperature over here, cold. They're in some contact, which is the way the heat transfer from high temperature to low temperature. All right. But something can happen with fluids that it can't happen with heat transfer. Here I have low pressure and I'm going that way into high pressure. Heat does not spontaneously transfer from low temperature to high temperature. Right? It's like one-way direction. But guess what happens in fluids? And this is why fluids is a hard class. A lot of people struggle with fluids. Can you have flow go from low pressure to high pressure? A nozzle makes it accelerate. A diffuser makes it slow down. And when it slows down, it builds pressure. From thermo as well as other classes, fluid mechanics. You can go from low to high pressure. But fluid particles don't like to do that. So this is what they call a favorable pressure gradient. They like to accelerate. Everybody's happy. This is an adverse or unfavorable pressure gradient. And so what happens is the fluid out here that has significant speed a little further away from the surface is okay, it can do that. But the fluid close to the surface doesn't have a high speed because of the no-slip boundary condition. And actually, in an adverse pressure gradient, it gets to the point where it gets to a stagnation or separation point, and then you get backflow, flow reversal, and then you start to get that recirculation on the backside of a cylinder. It all is coupled to this adverse pressure gradient. All right, so this is an adverse pressure gradient in the Stokes flow. It becomes really, really important when you go to higher speed flow because it will start to separate. The flow will separate. So I would encourage you, we do not have time right now, to play the same game with the turbulent flow, the high Reynolds number flow. And what's the difference? It's separated, and you have now a wake region behind. Okay. All right, how about this question? From B to C, there's an favorable pressure gradient, only for laminar, only for turbulent, or for both laminar and turbulent flow conditions. All right, let's take a look at what we got. It is true for both laminar and turbulent flow. It's both true. It's not exclusive to one or the other. Okay, from point C to D, down in here, going C to D, this is what they call an adverse pressure gradient region. All right. Is that true for only laminar, only turbulent, or for both laminar and turbulent? True for both laminar and turbulent. So if this is a turbulent flow with a high Reynolds number, this is laminar flow characterized by low Reynolds number. Why does the one have no wake? This is no wake region, no separation. And then why does one have a wake region indicating that there was some point at which it separated, then you have this wake? Why? Because it's when it's so fast that the magnitude of the static pressure, not the static pressure, the stagnation pressure is 1/2 rho V infinity squared, right? The stagnation pressure is a lot lower for the laminar flow case. It's a lot higher. So the magnitude of that pressure gradient is more severe, both the favorable as well as adverse. And because it's more severe for the turbulent, then you get that wake region. Okay. You can also, I'm skipping all these cases, 2, 3, and 4, but you get it for laminar where you get that recirculation as well. But the question is why does a very high Reynolds number flow get a smaller wake region? I think that was shown in the illustration, wasn't it? Let me see. Come on now. Find it right here. Doesn't this have a larger wake? And this have a smaller wake? But this is the higher, 5 is a higher Reynolds number. Why does it have a smaller wake? Because when you increase the flow, you can get it to become turbulent even in the favorable pressure gradient region before it gets to C. And if the flow is turbulent before it gets to the top, it'll actually be able to navigate and stay conforming to the boundary easier than a laminar flow. All right. How many people have ever played golf? Golf ball, you hit it and away it goes, right? In your image of a golf ball in your mind, is it a smooth surface or a dimpled surface? Dimpled. This goes all the way back to your high school education, but you're mechanical engineers, so in case you didn't get it in high school or get it in the physics class or get it in the fluid mechanics class, you can't leave this program because the electricals don't know this and the civils don't know it. It's your domain as a mechanical of why there's dimpling on golf balls. And what does it do to the fluid mechanics around that golf ball? And if anybody ever hit a solid, no dimpled ball, the same weight and everything like that with a golf club, it would not have the same trajectory and flight path if it was smooth versus the dimpled. Anybody ever try that? It's a good high school experiment. They'll take sandpaper and they'll just make it smooth and then they'll go do some stuff with it and you hit it. Maybe you can do that even at the college level in a fluids lab or something. Just play with it. But it'll have a different fluid behavior. So anyway, this is explained in this plot, but it's only way out here at this high Reynolds number. So if I characterize, this is the Reynolds number and this is the drag coefficient for cylinder or sphere. If we just focus on the sphere, that's probably a little easier, but you could see they have about the same trend. Let's focus on the sphere. Out in this region, you have low Reynolds number, you have Stokes flow, and there's no separation, there's complete recovery. But then you start to get separation, and the drag coefficient deviates from this simple analytic expression. But for a lot of it, when you get out in here, it's pretty flat. I know it does a little, but it's kind of like on a log-log plot, it's linear. Then there's a transition, then it's flat, and then out here there's a dramatic drop. So what's dropping? The drag coefficient. And the drag coefficient is related to the drag force, isn't it? Isn't the drag force C sub D times the area projected times the 1/2 rho U infinity squared? Okay. So you get this dramatic drop right in here. Even though you're going faster, it'll give you a lower net drag force. That golf ball will fly farther. But then as the ball slows down, the drag force kicks in more, and then it'll actually help it to try to slow down. So there's a lot of aerodynamics in golf balls. It's like, I'm going to hit you hard. I want you to fly really fast and go far. But as you start to slow down, I want you to sort of drop. And then if you have the right spin on it, when you hit the grass, don't just keep bouncing and go further, kind of stop. And it's incredible what people can do with a ball and a club. They could fly a long distance, and then it's like pop. And it pretty well sticks in that vicinity. So anyway, I guess I'm trying to compensate and try to help you learn fluid mechanics as well as heat transfer. I give up. Let's move on. I shouldn't have done that. I should have just said, here's our correlations. It's all empirical. Plug and chug. Oh, thank you, Professor. You're so good. One of the big questions is we just did a lot of work to get C sub D. Maybe that's related to C sub F. Maybe I divide that by 2. Maybe I come up here and stuff it into this analogy between heat and mass, not heat and mass, heat and momentum transfer known as the modified Reynolds analogy. But you cannot do that. You cannot just do that. You did it for the flat plate and it works. But you really just cannot do that for this problem of the cylinder, sphere, and cross flow. And the reason is the flow isn't steady, or the flow is more than one-dimensional. The flow has pressure gradients, so the flow has boundary layer separation. It's really C and D. And I'm just going to give you the answer to that. When you have a significant pressure gradient out there in the free stream, no. And then when you have boundary layer separation, no. But when you don't have those, this equation works well. So what they do is they just go and get empirical curve fits. So they say, hey, in this range of Reynolds numbers, use this value of C or this value of M in a very simple correlation for flow across a cylinder. And notice that they always have little footnotes. Pay attention to the footnotes. So they'll say this is for a Prandtl number 0.7 or above. This is good because that includes air and water. And most of our fluids are air and water. All of these properties are evaluated at T subscript F. What is that? What is that subscript F for? The film temperature, the average of the surface and the free stream. And you get these tables, the coefficients from the table. I don't like to do this, but I think this is the most effective way to help you learn. Well, okay, they have this empirical correlation based on experimental measurements. This person published a paper and blah, blah, blah. And so here it is. That's the same equation. Same Prandtl number, get them out of the table. And then right down here, the fluids are all evaluated at the film temperature. Fine. Then you continue to read. Other correlations have been suggested for the same problem. Welcome to heat transfer. So they say, this other person published a paper. That equation looks like that equation, does it not? It's very similar in structure. Here's some range of Prandtl number, range of Reynolds number. All properties are evaluated at T infinity, not the fluid temperature, the free stream temperature, except PR subscript S. What do you think that's a subscript S is there for? Because it's evaluated at the surface temperature. Those coefficients C and M, hey, that one has a C, that one's C, that's an M, that's an M, go out of a different table. What? So, right away, you don't know what the student's going to do. Oh, I need a C or an M. Oh, I'll go to this. Wrong, 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 wrong. Because this correlation works with that one, this one works with that one. So many places for error, right? So just be careful. The other, if you continue to read this, it says, oh, by the way, if you want a single comprehensive equation, somebody's done it. Look at that equation. Do you want to use that on a time-limited exam? No. But if you needed to, you could. But if you were programming up in a computer, well, program that up. It's no problem. So this one's great for computer. All properties are evaluated at the film temperature. So it's like option 1 for the same problem, option 2, or option 3. Which one's the best? They're all within 25% uncertainty anyway. It's fluid mechanics and heat transfer. It's empirical. All right. What happens if I have a non-circular cylinder in crossflow? So it has this hexagon shape or something. Well, in this range of Reynolds number, use this C and M, and this range of Reynolds number, this C and M, and there's a footnote with a lot of references to where they got it from. Ooh, in the textbook, one of my favorite lines in the textbook, it says, again, we caution the reader not to view any of the following correlations as that word. And so the clicker question is, what does this sentence mean? Don't trust these correlations, they haven't been verified by others, or do trust these correlations, they have been verified by others, or there is a typo in the book and that word isn't a word. Or these correlations have small uncertainty, or these correlations have large uncertainty. Which is it, the best interpretation of this sentence? Well, Professor, before we do that, I think that that sentence is not in the book. Oh, there it is. Right underneath that table. Again, we caution the reader not to. So it's sacrosanct. That's probably the best pronunciation. What?
That means sacred.
Sacred, yeah, not sacred, which means basically it's nothing about verified or unverified. It's basically a lot of uncertainty. These, right? So, okay, well, maybe I helped you in your reading. Okay. You move to a sphere, same game. It's going to be a lot of fluid mechanics, and then you wrap up an average Nusselt number, average convection coefficient. What's that over bar mean? Average. All right. And then here it's a correlation that's pretty popular. So this is good for a Prandtl number ranging from 0.71 to 380. Great, it covers water and air, a lot of fluids. Okay, but if you have a Prandtl number of 1,000, look for a different correlation. Or a Prandtl number of 0.001, look for a different correlation. Now, this is a question right here. What about this range of Reynolds number? Reynolds number diameter. Is that from 3.5 times 10 to the 4 to 7.6 times 10 to the 4? Or 35,000 to 76,000? Is that what that question? Is that what that means right there? Or does it mean from literally 3.5 to 76,000? Which one is it? What is this lower value? Well, it's for a sphere, right? And it's for the Reynolds number. And so we jump back to this plot. Okay, I can find the plot, maybe someday. This plot. Look at what's on the x-axis. Reynolds number. What type of scale is this? Linear or log? You can tuck a lot of data in there. So the high value of the Reynolds number for that correlation was at 7 point something times 10 to the 4. Is that around here? All right. And if you interpreted, is it down like 3 something? Is that, this is 10 to the 1, isn't that 10? This is 1, this is 2, this is around 3, a little lower. So is that the range that they say it's good for? Did that help? All right, I can find my slide. So it is 3.5. It looks weird. Okay. And then the range of ratio of viscosities. All properties at T infinity except mu sub S, and you see that right there. Again, this is a red flag. If you see PRS or mu sub S, essentially all of the other properties are evaluated at the free stream except that one at the surface. You ready to solve a problem? So we have a large, 20 millimeter diameter sphere made of steel. There's a property, conductivity, thermal diffusivity, and the mass density of steel. It's dropped into a large tank of water. So here's our tank. It's filled with water, and we take this and we drop it in, and it starts to fall. The sphere is initially at 360 Kelvin. And the temperature of the water is 280 Kelvin, and we're interested in the time it takes for the center of the temperature to get to 320. So maybe it falls down here, and then the center is at 320 Kelvin. Okay. The sphere may be assumed to quickly reach the terminal velocity in the water. What do they mean by the terminal velocity? Does that mean the sphere floats? You know, sort of like a dead person, deceased. It's a terminal case. No. So what is that terminal velocity? It's going to fall at steady state at a constant speed, and that's at that constant speed. It's our terminal velocity. How do we calculate that terminal velocity? Part A. And we calculate it to be around 2.1 meter per second. Complete review of fluid mechanics. And probably for the next exam, you're going to have a question. And it'll be Part A, all fluids. Part B, some heat transfer. There you go. This is Part A, all fluids. Part B, heat transfer. So how are we going to calculate that terminal velocity? So free body diagram, and so there's three forces on the particle. What are the three forces? Let me pause and walk around. I really want everybody to get this. Show me your three forces. Show me your free body diagram. Show me the equation. All right, so what we have is we have the weight coming down. We have FB, buoyancy force. And then we have FD, drag force. And so sum of the forces equal to 0. So what we have is we have the drag force, which is our drag coefficient, our projected area, 1/2 rho v terminal squared. That's our terminal speed squared. Then we have for the buoyancy force, I'm going to leave it like that, and the weight is a little easier. I'm going to move this up here. The weight will be the density of the steel, the volume of the sphere, and G. Isn't that our weight? Okay, so what about our buoyancy force? I forgot the equation for that. Rho v G. Now I ask the question, is the G the same as on this one in that term? Is the V the same as on this term and that term? Is the rho the same this term and that term? No. So we put a subscript on this row, S for steel, and this one W. I don't know what the W is for. For water. So the buoyancy force, you go back to, how do I calculate that buoyancy force? A lot of students are like, I forgot that. Is it Euler's principle, Bernoulli's principle, Newton's principle, Stokes' principle, Archimedes' principle? Archimedes. Archimedes. That's right, Archimedes. Eureka. All right, no time for that. So the problem is I have this image of the drag coefficient of a sphere. It goes like this. Where am I at? I need to get the Reynolds number. The Reynolds number is rho v terminal d divided by mu. I need to know the final speed to get the Reynolds number to get the drag coefficient. I can't solve this problem, Professor. What is that word? Iteration. Iteration. So what do? Is you probably would assume a drag coefficient because it seems like you're probably in this range of Reynolds number. So you go back and you say, I don't know, drag coefficient's about 0.8, 0.1. No, that's too low. 0.4. Okay, somewhere in that vicinity. And then you would actually solve for the terminal speed. Then go get the Reynolds number. Then come in and update your value of C sub D. All right. I loved playing on one of these in playgrounds when I was little. Do you remember this? How many people loved it? They banned them because they're too dangerous. But anyway, a little kid would be right here, and there'd be big kids pushing it, and it would go so fast you'd twirl off. Anyway, and when this was full of kids, and that's when I was playing, you had to try and get on. It was never stationary when I got on. And so you just have to run and jump in somewhere where there's a gap. Is that true? You remember playing with this? This was a lot of fun. This is fluid mechanics. Professor, I need to get C sub D, I need to get Reynolds number. Pick one. You'll get better at finding the gap. It's like probably for that problem, that's the one to pick because it's kind of flat. And then you'll calculate the V, then you can get the Reynolds, then update the C sub D, and if you like to do this again and again, but you're going to quickly see that one or two iterations, you're done, it's converged. Same thing when we get to heat transfer. It's like, I'm looking for the H. If I knew the Nusselt number, but I don't know the viscosity, calculate this temperature and the Reynolds number, you kind of like pick one and grab it and go. That's what I can say. And by experience, you know, the first time a kid plays on one of these, he probably comes home bruised on the merry-go-round. But after a while, you learn how to grab on and, you know, the same thing in heat transfer. Just find a place and grab on and make do. So let's go back to our problem. See what I'm talking about? That sphere was pretty flat in there. I would just grab 0.4, 0.6, 0.5, something in there and start. That's that part. Let's go to the next part, part B. What is the height of the tank that you needed to cool it? Well, professor, is this a class in dynamics? Because if the speed of the terminal is this, and I multiply how long it takes to cool it, doesn't that give me a height? Where's that equation in this textbook? You got to know something, right? So it's okay, you know. So basically, you're going to calculate the height needed based on the time needed to cool it. And the time needed to cool it, you can do it a couple ways. If it's lumped capacitance, you solve for that time. If it's not justified, you'll have a Fourier number. You unravel the Fourier number to get that time needed to cool. So I see I'm running out of time, so let me just say that based on the speed, which I don't have in front of me, you calculate a final height needed to be about 3 meters. Okay? A little over 3 meters of height of the tank for this problem. Thank you for your attention. I'll be in my office.